So we are going to move now for the talk of Kishan Deka. He will be speaking about the lensing of CMB modes with tomographic cross-correlation between LSST and CMB stage 4 survey.
Thank you. Good afternoon, everyone. My name is Kishan Deka. I'm almost a fourth-year student at the National Center for Nuclear Research in Warsaw. I previously worked on CMB delensing, foreground systematics, and constraints on tensor-to-scalar ratio. But today I'm going to be presenting about delensing of CMB B-mode coloration using the cross-correlation between CMB and galaxy surveys. And this work I am doing with my advisor, Pavel Bielowicz, and collaborators on the Stanford. So let's begin. To give you an introduction about CMB polarization, so we observed the polarization of CMB in two different components. One is called E-modes and one is called B-modes. And these two are basically imprints of primordial fluctuations. So E-modes are generated by scalar and tensor fluctuations in the primordial universe, and the B-modes are generated only by the tensor fluctuations. So these tensor fluctuations are predicted by inflationary models, and the inflationary models predict that there will be primordial gravitational waves, which will imprint tensor B-modes on the primordial CMB map. And cosmologists want to constrain this primordial gravitational wave amplitude, and the parameter they look for to constrain this amplitude is called tensor-to-scalar ratio, which is the ratio between the amplitude of tensor fluctuations versus the amplitude of scalar fluctuations. Currently, we have upper limit on this parameter R from Planck and Bicep, and it's about 0.032. But next generation CMB survey, they want to constrain it up to 0.03. Now, in this conference, there have been a lot of talks related to CMB lensing. I just want to specify here about one particular quantity, which is this phi, which we call lensing potential field. And this lensing potential field is basically the integral, line of sight integral of the gravitational potential that deflects the photons along its path. And this lensing potential field actually traces the dark matter distribution and the large scale structure over a universe. So just keep in mind this phi, because I'll be using it in my equations. Why we are interested in lensing is because in polarization, it's important to study this lensing B-modes, which is produced by the matter distribution that lies between last scattering surface and us. So the weak lensing actually twists the primordial E-mode pattern and generates some secondary lensing B-modes. And this is important because if we want to probe, let's say, the primordial tensor B-modes, we must subtract this lens B-mode signal because it's a secondary effect coming from lensing. If from this plot, you can see that this is plotted in power spectra space. So you can see that the lens B-mode amplitude is much higher than the tensor B-modes for different R values. So if we want to probe, let's say, R of the order of 10⁻�3, we must subtract this effect of lensing in the B-modes. And that's the whole idea of this field. Trace the CMB lensing field, the phi, subtract the lens B-modes, and then improve constraints on the tensor-to-scalar ratio. Now, how we do this delensing, as we say, how we subtract this lens B-modes, is basically, in theory, you can get a theoretical prediction of the lens B-modes by taking a convolution between the primordial E-mode and the lensing potential field phi. But we don't know the primordial E-mode, so what we take is the E-mode that we observe, which is also lensed, and we get a reconstructed phi from the CMB observation itself, and we convolve them and get a template for B-mode, which is not perfect, entirely perfect. It will give some residual B-modes, but still we can get an idea of the lens B-modes and subtract this template from the observed B-mode, and then we call the delens B-mode as B-del, let's say. Then we can get a better constraint on R, because that will subtract some of this power from the lens, from the observed B-mode. Now we have done this work in last 2.5 years. Basically, we were trying to study the impact of galactic foregrounds while constraining this tensor-to-scalar ratio. So we have created a pipeline for that. We have multi-frequency CMB maps with CMB plus foreground plus noise that goes to foreground cleaning. So we separate the galactic foreground. We get clean CMB maps. Then we estimate the lensing potential from the CMB observation. We get the lensing B-mode template. We delens the map, and then we do the likelihood analysis to get the tensor scalar ratio. And we studied it for different level of complexity of galactic foregrounds. So this was my first work of PhD thesis, and it's going to be submitted soon. But the topic that I'm going to talk about today is using other tracers of large-scale structure. So not only CMB observations, but I want to use, let's say, galaxy over density maps from LSST, and use that tracer to create a lensing B-mode template, then do the delensing pipeline again, and see if it improves the delensing efficiency. So we can define a quantity called correlation coefficient. The idea of this coefficient is basically you use the cross power spectrum between the lensing potential field and the tracer, and you get also the auto power spectra and get a quantity like rho L squared. The idea is that higher the correlation coefficient for a particular tracer, the better the lensing tool it will be when we use it in the pipeline, right? So what we do is we have generated simulation of LSST survey, like a galaxy catalog, and this redshift distribution comes from the official rail package of LSST survey. So we get this redshift distribution. We generate some maps in different redshift beams, which are correlated with the lensing potential field, also called as lensing convergence field. So here you can see that lensing convergence field, and all of these maps are correlated to each other by the input power spectrum. Now we divide our galaxy catalog in these redshift beams and use each of these redshift splitted maps as an individual tracer and combine them with optimal weight, and now use that tracer like CMB observation plus galaxy redshift beam splitted information. We combine it with optimal weights and get an estimate of the B-mode template and then do the delensing. And for this case, we again define a rho L, which is correlation coefficient. It has been mathematically formalized in Manjotti 2017 paper. And we check for what type of delensing method we get the highest rho L so that we can get the best delensing. For example, here you can see that if we use the LSST catalog as a full catalog, rather without like using the redshift information, we use it as a complete catalog and get one galaxy over density map, and use that for delensing. Then we'll get the lowest rho L, which means it will work as the worst delensing method. But if we split in redshift beams, which is this green line, it has higher correlation coefficients, which means it gives a better delensing method. And then the blue line is only from the CMB observations. So if we delens using only CMB observations, then we get somewhat good delensing. But ultimately, if we combine the CMB plus the LSST, the green one, we actually get the optimal delensing method that will call optimal correlation coefficient here. And we're going to try this with simulations. So we have like a set of simulations for about 50 correlated maps. And then we do it on the maps itself and check if our method is working well. So you can see that if we only use CMB data, CMB observations, then here it's the delens power spectra level. So this was the original power spectra for lens observed B-modes. And after delensing, using only CMB, we get to this level. But if we include also LSST data, we get better delens spectra. So the power is much reduced. And this will translate also to the uncertainty in the tensor to scalar ratio. So if we can delens more, we can get a better sigma of R, a better constraint on R. Here, I don't know if you could read, but these are like different methods that we use. The first one is without delensing. So we don't do any delensing, but just do tensor to scalar ratio constraints. This is obviously the worst. We do two separate LSST delensing. One is using the entire without the redshift information, full delensing. and also splitting it in redshift beams. This is LSST split. So, and this is only using CMB observation. And the final one is the optimal delensing method that I discussed using CMB plus LSST cross correlations. And you see that this optimal one gives us best sigma of R. And in terms of numbers, it actually improves by 20% compared to the CMB-S4 only like using CMB data. So this is all fun and games when we work with simulations, but in real life we'll have a redshift distribution error, which looks like this because of the redshift error in redshift, the uncertainty in redshift. The redshift distributions will look like this. So the edges of the beams will get wider, and there will be some cross correlations between the redshift beams itself, which you can see that there are some off-diagonal spectra between the beams that has some power now because of this redshift error mismatch. So we are working on this pipeline. So this was already ready with the CMB part. So we are now doing this photo-Z calibration part. And what we want to do with this pipeline is to propagate the error in the photometric redshift to tensor to scalar ratio constraints and see like how much it impacts the constraints on R. With that, I'm gonna put the conclusion slides here. So we tried to get the optimal delensing, and we are now starting to propagate the photometric redshift errors. And I also want to put it here that I'm looking for postdoc opportunities as it's my last year. So if you have any information, I'm happy to chat about it. And thank you for the opportunity to present it.
Question?
So if I've understood, you're doing the delensing at the power spectrum level.
No, actually we are doing it at map level.
You do actually,
Yeah.
Okay, because that sounds more general.
Yes, but like this, in this slide, the forecasting we did is coming from power spectrum level because we are still working on this pipeline here. But the first pipeline that I showed here, this our estimate, it comes from the lensing from the map level. So we have like 100 simulations of lens CMB, then delens, and then do the likelihood analysis with covariance metrics and get this.
Okay.
Sorry if you said this, but or when you make the template B-map from the LSST galaxies,
yes,
are you using just the numbers of galaxies or lensing also from LSST?
From LSST, we're just using the number, like the galaxy avoidance.
Oh, wait, this is my question. You don't need to make a B-mode map, you just need to make a displacement map. So you move the CMB pixels, and then you recompute the B-modes from the clean map. Isn't that what you do?
Sorry, I didn't understand.
Well, gravitational lensing moves pixels on the CMB sky.
Yeah.
What we need to know is those displacement vectors, so we can remove them.
Yes.
So you do
Okay.
you predict the lensing displacement, move the pixels, and then recompute the B-modes from the clean map. Isn't that?
So yes, so basically there are two methods that you can use to delens. One is this basically doing ray tracing kind of thing, you move the pixel, and another one is coming from the Fourier space expansion. So this is like a linear order approximation to the B-mode map. And it has been shown that this method works better because there are some cancellation in the terms when you expand it. And this method works better in terms of reducing the delens level after delensing. Yes, maybe we can talk about it. Yeah.
My question is, if you have the lensing from LSST, would that improve it further?
We haven't checked that yet, but okay, so we are interested in the redshift range of, let's say, 1 to 2. So if we can get an estimate of say like galaxy weak lensing in this range, a better estimate, then yeah, we can include that information in the delensing method as well, and it will maybe improve it by some fraction. So it's basically the idea is the more tracers you can add with the optimal weight, it will work better.
Yeah, it just wasn't clear to me. It's better to try to reconstruct this CLB lens potential from the number gains or directly from lensing of LSST and hydrogen, which overlaps in the CMB curve.
So for now, we're just using the overdensity maps.
It would be a good cross-check to do those independently to see if they agree. Rather than just combining them blindly.
Okay, so let's thank the speaker again.